Welcome back to one more video where we're gonna be optimizing something. And in this case, we're not talking about areas or volumes, minimizing, maximizing the size of whatever we're building. But we want to minimize or maximize the cost or the profit of the function. All of you, regardless of your majors, should always assume that at some point you will decide to build some kind of business. Why not? And for example, for your case, you will have to work with some mathematics, which will help you to optimize your model. And usually what do we want to do? We want to maximize the profit by minimizing the cost, right? So this is exactly a very good example of that. Let's figure this out. Step 1, carefully read the problem. Enclose a rectangular garden with area 1,000 square feet. One side costs $30 per feet. The other three sides cost $10 per foot. Find the dimensions in area that minimize the cost. I see. So I can build something huge like a mansion in this case, but then I will spend tons of money, right? And if this is my business or I'm trying to actually build that, I want to save money. So I want to minimize the cost of whatever I'm building. That's a very good example. Because if you're ever going to be a civil engineer or even a biologist or physicist or anything, for example, you got a grant from some kind of scientific group, say NASA gave you $5 million to build something, whatever you said you are able to build with your team. Well, this is a perfect case of minimizing the cost of whatever you're building. You want to make a good product, but you also have constraints on the money. And either they gave you amount of money and that's a constraint, or you're given the restriction of the size of whatever you're building and you want to minimize the cost. That's why it's always complicated. When the first smartphones showed up, people were checking out what the consumers like about smartphones. And smartphones had different shapes and some of them even had buttons below at the beginning. Then consumers start saying that I don't like how big it is. It doesn't fit in my pocket. Or the screen is too small. It's hard to read. Or the buttons are annoying. Or also they will complain that it is too slow. Or the battery is too weak and the phone dies too fast. All those are constraints. The person who builds, or the team I would say that creates a smartphone, had to take all those constraints into account, build a beautifully perfect smartphone for you, a consumer, but also to minimize the cost of whatever they're building. They don't want to spend a fortune for a beautifully good battery, right? To increase the lifespan of the smartphone and so on. So that's a very good example as well. Step 2, let's create a picture. I know how to draw a rectangular garden. I will make it this look like. And I also know something about rectangles. They usually have lengths and widths, and I'll write this down. L will be my length, and W will be my width, and both will be in feet. Again, make sure you have good notes. In the future, you will be a scientist, and it's nice that you have good notes. Then other scientists can read your good notes. Then I see that now area is given. So I can put it actually over here. Area is 1,000 feet squared, right? So area is given. If something is given, usually that's my constraints. But let's see, maybe that's not the case. I also given that I'm not talking about the size of the fence yet. I'm talking about the price of the building, the fence. And it seems like that one side costs more than others. For example, there are rocks over here. So since there's many rocks, I will have to dig more holes, and it just will be time consuming to hire someone. And that's why, say, this size will be $30 per feet. And that's just a guess. It actually might be this side, or this side, or this side. I'm not sure. It's a literally guess. And then math will fix our guess. Was the length actually the most expensive one to minimize the cost, or the width? The other sides will be 10 and 10 and 10. Okay, all in dollars. And now it matches the story. 3 sides costs $10 per foot. 1 side costs $30. Find the dimensions in the area, then maximizes the cost. So I will also find the minimum cost just because I'm curious, but actually they don't ask about that. Let's write down the objective function and the constraints in the given case. Constraints are usually easier to write down. Constraints here are areas. So area is given, that's 1000, and area is length times width. Remember the steps. Write down the function for the constraints using the variables you listed. Here they are, L and W. That's my constraints. Then, what is the objective function? Objective function seems to be a cost function, and I will call it C. Let's build the cost function. The cost function will be how long this side, L, times 10. Because if this side is L feet, and I need to pay $10 per foot, then this one side will be $10 per each foot, which is L. Makes sense? Then, what about left sides and right sides? I will have 10 times width for the left side, and then 10 times width for the right side. And then the expensive one will be, right, 30 times length. Make sense? And this is my cost function. Let's simplify it. Cost function becomes 40 length and 20 width. I'll put this in a box. That's my objective function. Those are my constraints I will use soon. So I will call it objective function and constraints. In this case, the number 2 was built first and then number 1 was built later, and here is my system over here. Don't forget to write down what you want to do with the objective function, to maximize it or to minimize. I want to minimize the cost. Here it is, it's saying that minimize the cost. This is my model. I would say it's my optimization model. So we're teaching you to build models. That's why when you see what kind of modeling experience do you have, and you can put in your resume that you indeed built some kind of models from the calculus class or maybe some summer internship or projects. Now what do? I want to minimize my function C, but C has 2 variables, L and W, and I don't know yet how to do it from calculus 1 class, so I want to get rid of one of these variables. Well, to do that, let's use 2. Use 2, that's my A. So the 0 step is to create a model. A, use 2 to solve for one of the variables, and choose the one you like more. For example, to be consistent, I will use my notes, and I can see that I don't know actually which one I did. I think I solved for width. Doesn't really matter. The width will be 1000 over L. Put it in the box, we will use it later because later at the end they will ask us to find the dimensions. That's both length and width. B, plug or substitute W into 1, or even not even put W, whatever you chose. So you can choose a different one if you want. Plug into 1. What is my 1? That's objective function. Then cost function, which is objective function, becomes 40L stays the same plus 20W. But W now in green color, here it is, in green color, will be 1000 over L. To simplify, C now becomes 40L plus 20,000 over L. And I want to minimize this. Minimize. Okay, I know how to do that. Also, there are some kind of restrictions, of course, on both length and width. Well, definitely these cannot be 0, right? And it will make it in the denominator 0. Also, from L times W equals 1000, we can figure out the domain for each, and so on. I don't want to do that. I actually usually avoid doing that, and I will explain you later how do I avoid doing that. But you should know, in different literature, they will explain you that you can find a domain and use closed interval methods if you want. I will just do what I know how to do. I will differentiate and find critical points. Before I will be differentiating, I highly recommend you to create common denominator if you are working with fractions. You will see why in a second. If you're working with some kind of piece that has a fraction in it and then you want to differentiate it later in order to find critical points, create a common denominator. I'm really saying you that's going to be much better. Multiplying by L, this first piece becomes 40L squared plus 20 thousandths, and that's my C. And now when I'm going to be finding the derivative, I will be using here quotient rule. Oh, I can see actually it's not very convenient. Okay, create common denominator later, taking my words back. I wanted to say it later, not right now. Let me do it this way. Don't do that. Actually, you can, but you will see it will be much longer if you do quotient rule now. C. Let's differentiate C. It will give you 40, derivative of 40L, that's 40, minus 20 thousandths over L squared. Did you catch how I did it so fast? I'll explain. This piece can be rewritten as 20 thousandths L to the negative 1. When I differentiate that, it becomes negative 20 thousandths L to the negative 2, or over L squared. And now, when you want to solve this for 0 in D and E, create a common denominator. That's what I wanted to say. Create a common denominator, which will be 40L squared minus 20 thousandths. This common denominator will allow you to avoid mistakes. Which mistakes I'm talking about? I'm talking about the mistakes when you don't include L in your critical points. Critical points are not only coming from zeros, but they're also coming from D and E points. So for the D and E points, L is equals to 0. That's my D and E solution, right? And it's not in a domain, so I can say not in the domain. That's why in this case it will not play a role, but in the future cases it might. And then the zeros are coming from the top of the fraction, 40L squared minus 20 thousandths equals to 0. So this quadratic equation, 40L squared equals 20 thousandths L squared equals 500, right? Do you know how to do it? This 0 cancels with this 0, so I have 2000 over 4. That's 500. Then L equals plus or minus a square root of 500. Don't forget plus minus, but 1 is not in a domain, right? So I only can use plus. L equals a square root of 500 is the only critical point here because all others are not in a domain. Let me point this out. The negative 1 not in a domain and the 0, 1 not in a domain as well. Nice. Now what do you want to do? First derivative test, second derivative test. You can take second derivative if you want. Actually, it's not going to be that hard. Closed interval, if you find the ends of the intervals, then you can do that. I will do first derivative test. That's going to be my D step. First derivative test tells me to write down the sign line for the C prime, put the only critical point I found in the domain over here, and I definitely know I can't go beyond 0, and there's some kind of upper bound as well for this problem, and you can find if you want, I told you. But what I'm going to do here, I will go into my derivative, which I wanted to put in the box and I forgot. I'll always recommend you to put the first derivative in the box and plug my test points into my first derivative. Let's plug test points. What is less than square root of 500 and 0? Well, I don't know what square root of 500 is. You can think about it. If you have something like 400, right? That's going to be 20, because 20 times 20 is 400. So it's something more than 20. And if you use your calculator, it's actually 22.36 or so. Well, it doesn't really matter. I can just use 1. I'm just saying, you can always put some approximate number if you want. Use 1. 40 minus 20,000 over 1 is definitely negative. Then over here, what is more than 22.36? I don't know, let's use some kind of number like 40. Then 40 squared will be 1612. And then you need to take your calculator, or even approximately, and check if 20 thousandths over 1600 greater or less than 40. Those two zeros go away. So it's actually 200 over 16. 200 over 16 is less than 40. You can even check, you just multiply 40 by 16. It definitely gives you more than 200. Then it becomes positive. And that's what we expected to have, because then it means the original function c, the cost function, was decreasing, it reaches its minimum cost, and then starts increasing. And now you just need to point out why this local minimum actually is global minimum. Several ways to see it. Since we don't have any other critical points on the right, we have only critical point on the left, 0 and minus square root of 500. They are outside of the domain. Then on the domain, from 0 to square root of 500, the cost function is decreasing. From square root of 500 to whatever the next point of the domain is, the cost function is increasing, and there's no other turns making, the function doesn't make any turns over here, because if it would, we would have a critical point from the equation, right? Since there are no other critical points after square root of 500, then there's no way it will go down and becomes lower than the minimum we just found. Mathematics tells us that there's no other terms going on after square root of 500. Then we can say it's global minimum. Then we can answer. What did we find? Did you remember it was lengths or widths? What is that? Lengths. Length is square root of 500, which is approximately 22.36 feet. Width, remember I told you put it in the box. We need it right now. Width is all over here. 1000 over L. 1000 over L equals, my L is square root of 500. And this is approximately, either you can leave it exact number like this, or approximately 44.73 feet. That's the answer of the question. The question told you, find the dimensions that will minimize the cost. That's actually good enough. But I'm a curious person, so I will do extra step. That's extra step, you don't have to do it. What is the minimum cost? Can I tell my client, for example, so how much he or she will actually pay for this project, which I said, I know exactly the dimensions of your fence, and this I promise you as a builder that will be the minimum cost for this project. Then I want to calculate C. C was 40L plus 20W, if you remember that. Let's check if you don't. You can also use this equation over here, 40L plus 20,000 over L, or the original one, 40L plus 20W. Plug in your numbers and you will find that the client will spend approximately $1,788.85. What's the units? Dollars, because it's a cost function. That's my minimum cost. Minimum cost. You decide. Minimal cost, yes. So this is how you work with problems with a cost function. Again, in the previous video, I told you that all the problems we're working on has graphs, and that's why we taught you to find concavity, increasing, decreasing. This problem is not the exception. I do have a graph for you. And here it is. It was hiding all this time. This is the graph of the cost function. In one variable way, it looks like this. 40L plus 20,000 over L. So let's say it's going to be 40L plus 20,000 over L. Since we have division by L, the graph looks something like this. Go check my video of the basic functions to make sure that you remember that. That's 1 over x graph, remember? So this is something like that. And we ask you to find minimum for this function. It doesn't have a minimum. As you can see, it's keep going down forever, over here and over here. But we worked on a domain. Seems like we cannot have 0 for our length or width, right? Or else we're going to have division by 0 for both cases. And there's definitely some kind of maximum value we should find if you really want to. So it means we're working only from here to some kind of maximum value. The most important part that it did reach its minimum somewhere over here. And we know actually where. This point over here is a square root of 500, which is approximately 22.36. And it matches really well the graph. That's my global minimum on the domain for this piece, for you to understand. And that's why I did not find the borders of the problem, the domain, if be honest. I know the L should not be 0, but the maximum, you have to solve it to find the maximum values for L. Well, I know it was decreasing before square root of 500. And then it's increasing forever or until the next side of the domain after square root of 500. So it's kind of a little bit waste of time to find those both points. I just need to know that it's decreasing before, increasing after, then the square root of 500, indeed my global minimum on this restricted domain. Like I told you, all the problems have graphs. And now since you're professional in graphing, analyzing the graph, finding concavity, inflection points, maximum, minimums, you can literally try to optimize all your life. From the diet to workout schedule to the perfect marriage constraints and so on. That's a joke, but you can try if you want. Hope you enjoyed the video and see you next time.